In this lesson, we're going to look at how we can incorporate the idea of a concentration of a solution into our stoichiometry calculations. So we've learned that we can have a value, the molar concentration, that can tell us about an aqueous solution. And we can use that molar concentration to convert between moles and volume. Right? So the molar concentration is the number of moles of whatever substance per liter. So we can use that as a conversion factor to go from volume to moles, or from moles to volume. Or you can use the formulas rearranged, right? So you can find moles by doing concentration times volume, or you can find volume by doing moles over concentration. But if you're given two of those pieces of information, either the volume and the concentration, or the concentration of the moles, or the moles and the volume, you can find the other value. Right? So if, as I was just saying, if you're given moles and volume, you can find the molar concentration using concentration equals moles over volume. So we're going to incorporate those calculations into our stoichiometry roadmap. Okay, so this is where we're at so far. So now we're going to add in solutions. So if you have a solution involved in a reaction, you might be given a volume of that solution. So you're told, 10 milliliters of sodium chloride reacts with, right? So you're given a volume. The other piece of information you'd have to be given is the concentration of that solution. And if you're given those two pieces of information, you can find the moles. So you can convert to moles using the concentration when you're given the volume. And so now you've arrived at moles. So then you might be asked for the volume of some other solution involved in the reaction. So you're going to use the mole ratio to go from moles of given to moles of unknown, just like we've done in all our other stoichiometry questions. So then you're asked for the volume of an unknown. Well, you know the moles. You'll be given the concentration in the question, so you can convert to volume using the concentration of the solution. The other thing that you might be asked for is a concentration of an unknown. So you might be given some quantities of some other reactant in the equation, in the chemical reaction, and asked, well, what was the concentration of the solution to begin with? So in that case, you've got the moles of unknown. You'd be given the volume, so you would just calculate the concentration using the moles and the volume. Okay, so now we're going to start to get questions where we may go from the volume of one solution to the volume of another, or the concentration, or we might have a mass of given and be asked for a volume of a solution. Okay, and I realize this is getting complicated, and I don't expect you to memorize it. What I want you to do is understand what's happening. So if you look on the left side of this map, all the arrows point to moles. Right? So your first step is to take whatever you're given in the question and convert it to moles. And you now have lots of different ways to do that, right? We first learned about using Avogadro's number, then we learned about using molar mass, and now we have another way using the concentration of solution. So whatever the number is you're given the question, your first step is to get to moles. Then you can use the mole ratio to get to your unknown compound. So the other one that's being asked about in the question. And then from there, you take one of those arrows and you either use Avogadro's number or the molar mass or the concentration. So let's look at some examples. So here's our first sample question. What mass of aluminum is required to react with 500 milliliters of a 0.100 mole per liter solution of H2SO4? And we have our balanced chemical equation here, which we need to do any stoichiometry problem. So here's some information that's given in the question. We have a concentration of H2SO4 and a volume of H2SO4. And in order to use that volume in subsequent calculations, we need it to be in liters. So we're going to convert that to liters. The question asks us for a mass of aluminum, which means we're going to need the molar mass of aluminum, which we can get from the periodic table. So when you go to solve the stoichiometry problem, you want to start with the given, right, which is the H2SO4, and you're going to start with the volume. Okay, you don't ever start with the concentration because it's the conversion factor. So we start with the volume from the question in liters. Then we're going to use the concentration as a conversion factor. Right? So that concentration tells us there are 0.100 moles of H2SO4 in every 1 liter. Okay, so we can set that up as a factor, right? 1 liter on the bottom because we're trying to cancel out liters, and 0.100 moles on the top. So now we're at moles of H2SO4. So the next step is going to be to convert 2 moles of aluminum because that's what we're trying to find. So we're going to use the mole ratio, which uses the coefficients from the balanced chemical equation. So we've got 2 moles of aluminum over 3 moles of H2SO4. So moles of H2SO4 cancel. We're now at moles of aluminum. The question asked us for mass. So we're going to use our molar mass, 26.98 grams of aluminum for every 1 mole. So moles cancel, we're left with grams, and we get an answer of 0.899 grams of aluminum. Next example. What is the minimum volume of 0.25 mole per liter magnesium chloride required to precipitate all the silver ions in 60 milliliters of 0.30 mole per liter silver nitrate? So this is a double displacement reaction where the magnesium and the silver are going to switch partners, and the silver chloride is going to come out of solution as a precipitate. So we're told that we have a concentration of magnesium chloride of 0.25 moles per liter. We need to find what volume of that we're going to have to use. We also have a concentration of silver nitrate and a volume of silver nitrate. We're going to need to convert that volume to liters so that we can do the calculation. So we take the volume of the given, which is silver nitrate, from the question in liters, and now we're going to convert to moles. And we're going to do that using the concentration. So we have 0.30 moles for every 1 liter. Liters cancel. Now we're going to use the mole ratio. So we're trying to find a volume of magnesium chloride. So we're going to convert to magnesium chloride. So 1 mole of magnesium chloride for every 2 moles of silver nitrate. So those cancel. So now we've reached moles of magnesium chloride. So now we need to get to volume, and we know the concentration. So we're going to use that concentration as a conversion factor. This time it's flipped over compared to when we used the silver nitrate concentration, because we're trying to find a volume. So when we calculate that out, we get 0.036 liters of magnesium chloride. Often questions like this will specify that they want the volume in milliliters. Didn't in this case, but if it did, it would be 36 milliliters. Another example. Student reacted 100 milliliters of a silver nitrate solution with excess copper. So here we have a single displacement. When the reaction was complete, she collected all the silver and dried it. The mass of the dry silver was 1.65 grams. What was the molar concentration of the silver nitrate solution? So in this case, we're starting with a mass of silver, and then we need to find the moles of silver nitrate so we can then calculate the concentration. So the mass of silver that was created was 1.65 grams. We're going to need the molar mass from the periodic table. We know that the volume of silver nitrate solution was 100 milliliters or 0.1 liters, and we're trying to find the concentration. And we know that concentration is moles over volume, so we need moles. Right? That's our first goal. So we'll do the stoichiometry. So we start with the mass from the question, the 1.65 grams of silver. We're going to convert that to moles. And this time we're going to use the molar mass because we have a mass. In the previous two questions, we used the concentration because it was a solution and we were given a volume. But this time we have a mass, so we're going to use the molar mass. So we know that the molar mass means that there's 107.87 grams in every 1 mole. So grams cancel, and we now have the moles of silver, but we're trying to find the moles of silver nitrate. So we use the mole ratio, which in this case is 2 to 2 or 1 to 1. So that's not going to change the value. So when we calculate that out, we find that we had 0.015296 moles of silver nitrate. That's how much would be needed to make all that silver. So now that we know the moles and we have the volume, we can calculate what the concentration was. We just divide the moles by the volume, and we get an answer of 0.153 moles per liter. Let's look at another one. There's lots of different variations of these questions. When excess aqueous lead 2 nitrate was added to 125 milliliters of a solution of sodium iodide, a bright yellow precipitate of lead 2 iodide formed. The dry precipitate had a mass of 4.13 grams. What was the concentration of iodide ions in the sodium iodide solution? Okay, and so I have that bolded and underlined because that's key. Right? We're looking for the concentration of the ions, not the concentration of the compound. So, since we're trying to find a concentration of iodide ions, it makes more sense to use the net ionic equation in this case. Right? In the last lesson, we learned about how the net ionic equation is actually a representation of what is actually happening in the reaction vessel, right? So because we're asked for ions, we can use the net ionic equation. So in this case, the precipitate was the lead 2 iodide. So the reaction that actually happened was the lead ions from the lead 2 nitrate and the iodide ions from the sodium iodide reacted to make the lead 2 iodide. So we're going to use that instead of the balanced chemical equation. So some of the information we were given, so we know we have a mass of the PbI2 of 4.13 grams. We can calculate the molar mass of PbI2, 461.0 grams per mole. We have a volume of solution of 0.125 liters, because we convert the milliliters to liters. We're trying to find a concentration of iodide ions. And in order to find the concentration, we need moles to divide by volume. So what we're doing first is finding those moles of I-. So we start with the mass from the question, the 4.13 grams. Remember, our first step is always to convert to moles. Because we have a mass, we're going to use the molar mass to convert to moles. So the grams cancel. We're left with moles of PbI2. We're trying to find the moles of I-. So we're going to use the mole ratio from our net ionic equation, which tells us that there are 2 moles of iodine for every 1 mole of PbI2. So when we calculate that out, we find that there are 0.01792 moles of iodine. We know the volume, so we can calculate the concentration by dividing the moles by the volume of 0.125 liters, and we get an answer of 0.143 moles per liter. So those are 4 examples of questions that can be solved with solution stoichiometry. So adding that concentration idea into our stoichiometry framework. Okay, there are tons of variations on where the solution information comes in and how what the question is asking for. So please make sure you're doing practice questions so you can start to get a better handle on how these things work.